All right, we're going to work through problem number 3 first in using this problem solving sheet. So before I do it and you watch this, go and try it for yourself. Come back and check your work against mine. I will then do the solution to numbers 4 and 5 in the same way. So you will check your work. All right. So number 3, we have a grocery bag, right? It's being lifted up. So we have a bag of groceries, however you want to draw that, right? And we have these handles on it. We can assume that, some type of bag like that, right? So again, you go back and you ask yourself what forces would be present. The bag would definitely have weight, right? So we can include weight. If it's being lifted, there would be no normal force on it. So no normal force. It's not sliding past anything, no air resistance. There is an upward force. I'm going to call that upward force an applied force, or because they mentioned straps, you might have called it a tension. But I'm going to call that a force applied. That one's hard to see. I'll just go back this way. And that's going to be our force applied. No other special forces. So in this case, our free body diagram is we have a force applied and we have weight acting straight down, right? Now, we do have acceleration. We're told it is lifted from the floor to the table with an acceleration of 5. So will the sack hold or not? So what we do know is we do have acceleration in the upward direction. We're going to lift it. I'm going to take up as positive and down as negative. We don't have to worry about the y or the x direction in this case. So remember, before we move on, we are going to make Newton's laws. So always just get into the habit of saying summation forces in the x equals max, and summation of forces in the y equals may. So this is all taking place in this first box. You draw a picture, pick out your directions of positive and negatives, and then we're going to make that picture fit into Newton's laws. Since I don't have anything in the x, I'm going to go ahead and just say not needed. So non-applicable, right? All we have to worry about is the y, and in the y, we're going to say, you could say negative w plus force applied equals may. You could also write that as force applied minus W equals may. Now, under what do we know and we want to know? We want to go through and take a look at all the variables that we know and what are we looking for here. So it says the maximum force that a sack can withstand and not rip is 250. So what we want to say is that the force applied max is 250 newtons, right? The mass is 20 kilograms. And I know that's the mass because these are the units of a kilogram. And we are going to accelerate it with an acceleration of 5 meters per second squared up. So we do want to keep that as positive. So I already took even in acceleration, positive and negatives give us a direction, or we need a direction for acceleration with positives and negatives. The ultimate question is, will the sack hold? So in order to answer, will the sack hold, what I'm really looking for here is what is the force applied? That's my question mark. So I need to find what is the force applied, and then I will compare it to the 250 to say yes, it'll hold or not. Okay, so that's one way to do it. You can also use the force applied for maximum and see what acceleration you would get and compare the accelerations. I'm going to do it with finding force applied. So with those two boxes complete, the next thing is we want to say, well, what's our starting equation? So of course, if I'm looking for force applied, the only equation that contains force applied is this. So I will write force applied minus my weight equals may. And I go through and I say, well, I need I'm looking for force applied. I know mass, I know acceleration. I do not know weight. So off to the side, I also need to say, we also have to use weight equals mg. So this equation is good to go. Don't need that over there. But this one I'm going to rearrange because my force applied is not by itself yet. So my force applied minus weight equals MAY. To get force applied by itself, I'm going to add weight to both sides. So we would say plus W on both sides. So my force applied is going to equal MAY plus W. Now I'm ready to solve. So the first thing I can solve for is weight. Weight equals mg. So my weight equals 20 kilograms times 9.8 meters per second squared. So my W equals, I believe, 196 newtons. Sorry, I gotta get out my calculator here. All right, therefore, and don't worry if your work bleeds into the other boxes, not a big deal. It's just really holding you accountable to these steps. So now I will say my force applied equals MAY plus W. So that is 20 kilograms times 5 meters per second squared plus 196 newtons. So remember, I broke up a newton was a kilogram meter per second squared. So this actually ends up with the same units. We will have force applied equals 100 newtons plus 196 newtons. So for me to lift it with that acceleration, I need 296 newtons applied. So that is too big. So since that is greater than 250, the answer is no, it will rip. Okay, so the back, whoops, putting that in the wrong spot. Sorry about that. No, it will rip. So the verification, so that's really there for you to just say, is that reasonable? I would say 296. If I got 2096, then I think maybe I did something wrong if they're saying it back and hold 250. So I think I did everything good. The 296 is more than the 250. Now, how could I make it work? So this is an interesting concept. I can make the bag hold if this is smaller. I can't change the mass. That's not going to change, right? Therefore, the weight doesn't change. So the only thing I control is the acceleration. So when you quickly pull something up with a greater acceleration, you do have a greater chance of things ripping. If you're patient and you slowly lift things so they have less acceleration, more than likely they won't rip. So that's something you get out of that problem. All right, that is number 3. All right, we will continue on. Let's see if it'll let me open up another sheet. Probably won't because I have to. Okay, give me a minute while I open up another blank problem-solving sheet. See, I think we'll want to, oh shoot, didn't want to do that. Let's see if it'll say that in a different way.